Nowadays, we have a lot of good chips, advanced chips, with very high communication speed. How can they achieve such high communication? With the help of serial communication instead of parallel communication. If you are interested, please study the serializer, deserializer, the so-called SERDES. Yeah, here, right? If you're interested, you can study it by yourself. Anyway, I would like to tell you that nothing is free for such kind of high-speed serial communication. It is really power hungry. It consumes a lot of power, even for only one IO bit, right? And you can see for such kind of serial communication, it means it can transmit only one bit or only one symbol at the same time. It cannot transmit two or three. No, sorry for that. So it means for the chip, we need a lot of I/O pins for such kind of high-speed communication. However, pins are expensive part of the system. We need pins for many of the connections, not only for communication, but for your power, your VDD, your VSS, for gathering, and how many you need, for example, for power or ground. It depends on how much power the chip consumes. For high power chip, usually we need hundreds of pins for only VDD and ground. You can see how expensive the I/O pins will become, right? So pins nowadays become the bottleneck of the system, and we need to pay attention for such kind of high power I/O pin, especially for serial communication. For example, those are two serial I/O pins, and for B, the content is exactly the same. I mean, for previous clock, it is 1. And for the next clock, it is also 1. What you would expect the output waveform for B? Actually, it should look like this, right? All 1 before the rising edge and after the rising edge of the next clock. However, for pin A, actually it turns from 0 to 1. How can you make the output become 1? It means the PMOS of the upper buffer needs to be turned on and the output will be connected to the VDD, right? However, it needs to consume extra more power, more current. According to the Lenz's law, inductor actually hates the current change very much. So it will try its very best to stop such kind of fast current change. Nothing is free. If inductor would like to stop such kind of phase changing for current, it needs to pay the price for voltage variation. It will cause huge voltage variation as the price to stop fast current variation. In this way, pin A or upper buffer A and upper buffer B both are connected together according to the huge voltage variation. Not only A can see it, but also B can see it. And for the output of B, it doesn't look like this. No, sorry for that. B will see a big jump according to A's variation. Wow, that is really, really dangerous. For example, if you switch 16 output drivers at the same time, it can cause a huge voltage drop as large as 1.5 volt. Nowadays, how much supply voltage you have for such kind of advanced chips? Usually, for the core voltage, only 1 volt or even less. Wow! How can 1 volt VDD tolerate such kind of 1.5 volt huge voltage drop? It doesn't make any sense, right? So you need to prevent such bad situation to happen. It means never connect 16 output drivers to the same supply voltage. No. What's our recommendation? Usually 5 to 10, right? Let me check. Oh yeah. So typically for such kind of high-speed IO drivers, the maximum number to consume the same VDD or to connect to the same ground, the maximum number is 5 to 10. No more than that. Otherwise, you need to face such kind of huge drop. Then don't expect the receiver to the output of B will get the correct data. No, because here, for such kind of big drop, it looks more similar to 0 than 1, right? It is closer to 0 than 1. Then it may make the receiver connected to the upper buffer B will get wrong data. That is, it doesn't make any sense. Okay? And this is the reason why, again, I warn you, 16 output drivers connected to the same VDD or ground doesn't make any sense. You need to reduce the number to be connected altogether, right? The maximum number of them is around 10. No more than 10. Good enough. Why we have such kind of big voltage drop? We call it LDIDT problem. Yeah, the more inductance, the larger voltage drop you need to face. The faster change of the current, the larger voltage drop you need to face. So how to solve the problem? You either reduce L or reduce the IDT. It means you need to slow down the change of the current. If not, you need to face the big voltage drop. That is what I recommend. So you can see if you have inductor for such kind of output voltage variation, you will see the inductor will try its very best to reduce the current change, right? The current variation. Without the inductor, the current can change very fast, but with inductor, it cannot. But the price, as I mentioned, the price is you need to see such a huge change in terminal voltage of the inductor. Okay? It will cause a huge voltage drop at the output. It is not okay at all. So, as I mentioned, you either reduce L or reduce di over dt. If not, the other possible solution is to have coupling capacitor. Yeah. If you have coupling capacitors to stabilize the ground and VDD, then it helps a lot. Because the operation of capacitor is reversed to the operation of inductor. They can cancel the impact of each other. For example, L hates the fast change of current, but C hates the change of voltage. It means capacitor can help you absorb the voltage drop very, very much during such kind of LDI dt impact, right? That's it. You can see with the coupling capacitor, not only the current variation, but also the voltage variation can be reduced very much. But you need to pay the price. What kind of price? Large enough decoupling capacitor. Got it? Let's go further. You may be curious how much current we need to operate. Maybe if the current is not large. For small current, no much change you need to face, right? You can reduce the magnitude of the current consumption, but it is not true. Why? For our chips, for our mobile phone, notebook, or even for desktop, they are power hungry. They consume a lot of power. If you have a look at the specifications of all those powerful chips, they are power hungry. Yeah. How much power? Usually at the order of 100 watt. Wow. What? Because as I mentioned, nowadays the core voltage for such kind of powerful chips usually less than 1 volt. It means the current is more than 100 amperes. Wow, it's beyond my imagination. How about yours? That is too huge. For our own design, usually we focus on milliamperes, tens of milliamperes or hundreds of milliamperes. But for such kind of powerful chips, they need to tolerate more than 100 amperes for the current. So, as I mentioned, you need to face the consequence. Not only the current is so huge, but the change is also very fast. Why? Because our chip nowadays operate at gigahertz, right? So they turn on or off the gates, the switches very, very fast at gigahertz order. Wow. It means di over dt is so huge, it's totally beyond your original imagination. We need to deal with such kind of big problem. But how? How can we deal with it? As I mentioned, don't power all of them with the same VDD or ground. It doesn't make any sense. Typically 5 to 10 I/O drivers per supply pin. It will be good enough. And you need a lot of pins for such kind of I/O drivers. Not only, but also the VDD and the ground. Totally for Intel CPU, to my memory, maybe around 50 to 40% of the I/O pins are for VDD and ground. Blah blah blah. Oh. And how many pins Intel CPU has? Right now, I guess more than 1,000. So it means maybe 400, 500 of pins for such kind of I/O or VDD ground. Wow. Anyway, under such kind of serious condition, high power, big current, you need to try your very best to reduce L. So multiple pins, it means what? You can reduce the inductance because for inductor, many of them connected in parallel, the inductance will be reduced. If you connect capacitors in parallel, then the capacitance will be increased, right? On the contrary, the inductance and resistance will be reduced substantially by parallel connection. So it is another strong reason why we need a lot of I/O pins, to reduce L. However, never mind how many pins you try to connect in parallel, under current situation, the LDIDT is still too much. So we try to reduce L by parallel connection, and then many of them, hundreds of them connected in parallel, then you can reduce the L very much. However, it is not good enough. We need to reduce DI over DT also. But how? You need to increase the rise and fall time. That is another warning for you guys. Don't do any kind of over design, especially for students on campus. They would like to have perfect waveform. For the digital communication, digital signal processing, blah blah blah, all of them, you have 1 and 0 for the output, right? So the students would like to see some waveform like this. Oh, perfect, right? You have 90 degrees for the turns. 90 degrees here, 90 degrees, 90 degrees. It looks beautiful, but in performance, it is so ugly, because for such kind of very fast change, the IDT reaches infinite. It is really bad for your voltage drop, right? So on the contrary, you need to slow down the rise or fall time as slow as possible for your design, right? Only if it fits your specification, you need to slow down the rise and fall time. All right, don't try your very best to speed them up. If you would like to make such kind of sharp rise or sharp fall, it means what? It means you need a lot of power, a big current for that. You consume more power, more area, but you worsen the LDIDT problem, right? It doesn't deserve. So again, don't do over design. Don't do over design. Good enough means enough. More than good enough means really bad for your design. That is the problem of over design. For new students, new engineers, usually they are quite ambitious. I would like to make the best on earth, blah, blah, blah. So they would like to design such kind of very beautiful upper waveform. But pay attention to this. Never make any mistake in your future. Never. And also, the other solution is to carefully select the positions for your VDD and ground. For example, this is the DIP, the package called DIP, DIP, dual inline packaging. Okay. For VDD or ground, you had better select the shortest I/O pin. Oh no, the I/O pin with shortest bonding wire. Okay, because the longer bonding wire, the more parasitic inductance. Usually, we estimate that one, let me think, maybe 1 narrow Henry for 1 millimeter bonding wire. That is to my memory. Okay. Anyhow, the longer bonding wire, the more inductance you need to face. So please select the I/O pins with the shortest bonding wire for your VDD and the ground. That's it. But you can only apply such kind of proper selection for small chip. I mean, you may only have one pin for VDD, the other pin for ground, right? So it means what? The consumption current is not so much. For large chip, for powerful chips, they consume 100 amperes or even more. You need hundreds of I/O pins, so it is really hard for you to select. Anyway, careful selection is only good for small chip. All right, it means for the chip consumes very little current. You can make it in this way. If you try everything, parallel connection to reduce error, to slow down the rise or fall time, for di over dt. If it is still not enough, then you need to consider decoupling capacitor between the VDD and the ground. Right? It looks like a second order low pass filter to help you stabilize the voltage. Yeah. It is required for high performance circuits, just like DEC alpha. It has 128 nanofarad. Wow! It is NF instead of pico. It is narrow instead of pico. Nano actually is 3 orders larger than pico. For my students, if they use tens of picofarad, I will say, oh, that is really expensive. If they use more than 100 pico, I will say, hey, don't waste my money, right? Sorry for that. Oh, for DEC alpha, it used more than 100 nanofarad for only decoupling capacitor. It is money wasting. Maybe this is one of the reasons why DEC alpha was out of the market long time ago, because it is too expensive. All right. Anyway, anyhow, I will only like to recommend to use proper size for your decoupling capacitor. That's it. However, as I mentioned, the chips consumes more and more power, larger and larger current. It means what? The decoupling capacitor becomes larger than before. That is our destiny. Sorry for that. Yeah. Not for the bonding wire. It has not only parasitic inductance, but also parasitic resistance. We call it, the impact is called IR dropped. Again, V equals IR. The current by the resistance means the voltage drop between the two nodes of the resistor, right? So the more resistance of the bonding wire means the more voltage difference from the off-chip VDD and on-chip VDD. Wow. It will cause you a lot of problem. For example, if you would like to limit the voltage drop by 5%, then you need to make sure the resistance for your bonding wire needs to be less than 0.00005 ohms. It's really small. Again, with only one bonding wire. Sorry for that. The resistance is much higher than this. So what you can do? Again, multiple I/O pads, multiple bonding wires connected in parallel. You can reduce not only the parasitic inductance, but also the parasitic resistance. Yeah, it means you can solve the LDI dt problem and IR drop at the same time with multiple I/O pins, multiple bonding wires. However, you need to pay the price, much higher price, much more money for such kind of parallel connection. Okay, even you make it, you can see according to P equals IV, or I square R, or V square over R. For such kind of simple calculation, you will see 5 watt is dissipated by such kind of bonding wire already. Hey, totally for the chip, you would like to consume 100 watt, right? But even according to such small resistance for the bonding wire, it still consumes 5 watt. Wow! So it means you have only 95 watts left for your core circuit. Anyway, I will only like to warn you again. The parasitic inductance and the resistance, both are really harmful for your chip. So try your very best to reduce all of them. And again, as I mentioned, the easiest way is to connect multiple pins, bonding wires in parallel. Yeah. How to distribute your VDD and ground to your core circuit? In the past, for very small chip, we have such kind of structure. Yeah, for each block, very few blocks, right? And for each block, it has its own VDD and ground. That is in the past. Nowadays, we either have power grid or dedicated VDD and ground. What is power grid? Just look this. You have a lot of voltage, a lot of connection, a lot of the lines for VDDs, right? And a lot of the other lines for ground. It means for each block, for example here, right? You have two connections to blue VDD lines and two connections to purple ground lines. Good enough for usual application. However, if your chips consumes even more power, then you need to apply such kind of dedicated VDD in the ground. It means it looks like this, but with much more than 2 blocks, and each block needs to have its own VDD and ground. It will be more expensive than power grid. It's up to you. If possible, I think power grid is a reasonable solution to distribute your VDD and ground to all the blocks of your circuit. However, if the blocks need to consume even more power, then you need to spend more money and go for dedicated VDD and ground. It is really expensive. Okay. The other problem is, as I mentioned, with multiple parallel connection, we can reduce both the L and the R, right? The parasitic inductance and the parasitic resistance. Even though we still need on-chip decoupling capacitor to stabilize the final VDD and ground, the internal VDD and ground for your core circuit. In this way, especially for nowadays, as I mentioned, the inductor is really huge. The capacitor is even larger than before. So for such kind of LCL tank, it may resonate, okay, with the resonant frequency here, right? The problem is, in the past, we need only small capacitor, so the resonance frequency is really high, far beyond the operation frequency of your chip. However, nowadays, the decoupling capacitor, on-chip decoupling capacitor, is so huge. So it means what? The resonance frequency is reduced. If you are not careful, then the resonance frequency will be too close to your operation frequency. Then it will cause some kind of resonance. okay, between the VDD and the ground. Resonance for the VDD and the ground means what? They are not DC values. No. You will see some kind of fluctuation according to such kind of LC tank resonance. Wow, it's really harmful for your chip operation, right? Nobody would like to see this. So, what lesson you learn from here? You need to make sure the resonance frequency needs to be far away from your operation frequency. Okay, it can be much higher or much lower, but never be close to your chip operation frequency. Otherwise, you will cause a lot of trouble by resonance. Power supply resonance is really harmful. 因为目前的那个晶片越做越大，速度越来越快啊，所以说呢，我们刚刚在讲的那个解耦的那个电容，它现在也越来越大嘛，因为电流越来越大。那 LCL 这种谐振槽，它的谐振频率就是这个东西啊。问题来了，现在 L 跟 C 越来越大，所以你的那个谐振频率越来越低嘛。哦，在以往哈，我们的操作频率在这边哦。重来。在以往啊，这个是我们的那个晶片的操作频率，然后呢，你的那个谐振频率是远远超过我们的那个操作频率啊。不过，如同刚刚所讲的，因为 LC 越来越大，然后你的操作，所以你的谐振频率在变小。问题是我们晶片操作频率在提高啊，所以沙粒跟哈利终于要碰面了啊，他们碰面你就有大问题啊，它会产生谐振所以你的那个 VDD 跟 ground 看出来就不是两条平行线哦，他们就会抖，因为谐振的缘故，他们就会抖。那么谐振频率跟你的操作频率越靠近，他们就会抖得越厉害，这是你需要非常小心的地方通常是你做完后模拟，你才会知道你的杂散电容是多少嘛。你加总起来模拟一下你的那个谐振频率希望你不要中大奖。如果中大奖怎么办？要么你再多加一点，让你的那个谐振频率变得更低远离你的那个操作频率不然的话你就只好降频了，你的操作频率就是不能那么高OK, I would like to highlight the problem again. For current situation, we need to face more and more LC. It means the resonance frequency actually is lowered. However, the operation frequency of the chip is increased. So it means they become much closer to each other than before. So more likely, your VDD and ground will resonate according to such kind of LCL tank. All right, you need to be very careful. But how much frequency for your resonance? You can only simulate it after layout, because after layout you will know how much parasitics, blah blah blah. After that, if you find your resonance frequency is too close to your operation frequency, what you can do? You either get even more capacitor for decoupling to push the resonance frequency lower, much lower than your operation frequency, or you can lower down your operation frequency to make it far away from your resonance frequency. Anyway, anyhow, it's up to you. Okay, make the right decision for your chip. If you have any kind of fluctuation, resonance over your VDD or ground, then you will see the impact called jitter. Why? Because, for example, that is for ideal one, right? Ideal VDD and ideal ground. However, with such kind of resonance, okay, or variation, okay, spikes anyway. You can see here the VDD becomes lower, but the ground becomes higher. So it means the difference between VDD and the ground becomes smaller than the ideal value. Smaller difference, it means smaller driving capability. It means the propagation delay of the gate will become longer, right? On the contrary, for here and there, the power supply becomes larger than normal, right? Larger power supply means what? Better driving capability. Also means shorter delay. So, for the output waveform, according to such kind of variation, sometimes the delay becomes longer. Sometimes the delay becomes shorter. So the waveform, they cannot be overlapped. I mean the periodic waveform. From the input, then to the output, you will see, sometimes the output get larger delay here. Sometimes it get smaller delay there. And the variation is called jitter. Okay? It means the more fluctuation or resonance over your power supply, the more jitter you need to face. It is not good for your circuit. So this is another strong reason why you need to have the decoupling capacitor to stabilize your power supply, to reduce the fluctuation for your VDD in the ground. All right? That is the main function of our on-chip decoupling capacitor. I say here, okay, for all those slides I show you, actually, all of them discuss the on-chip capacitor. But except for on-chip decoupling capacitor, we still need off-chip decoupling capacitor, because from our power supply, if the power supply is good enough, right, the output voltage should be stabilized here. But the power supply needs to be connected to your chip through the wires on PCB. For PCB wires, they also have parasitic inductance, resistance, blah, blah, blah. So even though the output of the power supply is stabilized, after going through the long PCB wires to your chip, the voltage here is still fluctuated. What you can do to stabilize the off-chip VDD, the VDD and the ground just out of your chip. How to stabilize it with off-chip decoupling capacitor? Okay, then even you stabilize the off-chip VDD and the ground, as I mentioned, the bonding wire, the parasitic inductance of the bonding wire will also destroy the on-chip VDD and ground. Okay, so you need on-chip decoupling capacitor to stabilize the on-chip VDD and ground. That is the fundamental requirement for any kind of high-end system. Yeah. And this is what I say, power supply resonance is really dangerous. Try your very best to push your operation frequency for the chip and the resonance frequency for your power supply as far away as possible.